So we're starting chapter 7. This is section 7.1, which is on page 490 in your book. Our objective for today is the student to be able to write and evaluate exponential expressions to model growth and decay problems. So, we've worked with functions all year. Today we're going to be working with exponential functions. In exponential functions, where now we have the variable in the exponent, which we've not worked with before. So we've got the f read, the function of x is defined as b to the x power, where the b will represent the base and the x is the exponent. Asymptotes we've worked with before this year. Remember, an asymptote is a line that the graph approaches and gets closer to, but it will never touch that. So it will get closer and closer to that boundary line without ever crossing that. So we've worked with those earlier in the year, and you'll see them again in this chapter. So, exponential growth. When something is growing very quickly, like you'd like your finances to grow exponentially, they can be written as f of x equals a times b to the x power. And it's exponential growth if a is greater than 0 and b is greater than 1. Okay, and so that will be an example of exponential growth. So we can look at a problem here. The function of x is defined as 1.5 to the x power, where our a in this case is 1 and b is 1.5. And if we made a chart, we plug negative 2 in, 1.5 to the negative 2 would be 0.4. Negative 1, or 1.5 to the negative first power would be 0.8. Remember, anything to the 0 power is 1, and then so on. So 1.5 to the first is 1.5, 1.5 to the second is 2.25, to the third is 3.375, and to the fourth is 5.0625. So you can see I've graphed that over to the side. And if we were to connect this, you can see that it would go something like this, where it will continue up. We can put any value for x in, and it will continue up to infinity. But as we approach here, you can tell we could never get a negative number. And so if we were to draw in a asymptote right here, it would go right here on our x-axis, because we'll get closer and closer to that line, but we will never actually touch that line. Right, so that would be an example of exponential growth. Exponential decay, again, it's the same format, but you can see if x is greater than 0 and b is now between 0 and 1. Then we have a case of exponential decay. So let's look at one of that type. So now you can see a, again, a can be anything. So a in this case is 30, but b is now between 0 and 1, which tells us it's exponential decay. And as we plug it in again to the chart, to the negative second power we get 46.875. To the negative first power we get 37.5. To the 0 power we get 30, because remember 0.8 to the 0 is 1 times 30 is 30. And then so on. To the first 24, to the second 19.2, the third power 15.36, and to the fourth power 12.288. And again, if we were to graph this, I've dotted those points in there. You can see it would go up. Again, we can put anything in for x, and it would go up to infinity. But as I come down here, it would get closer and closer, but it would never again cross the x-axis. And so we have a horizontal asymptote there that it's going to get closer and closer to, but never cross. So that's an example of growth and decay of this format. Now we have another type of exponential decay we can look at, and growth. And this is what you use these formulas when you have a percentage rate, like maybe the value of something is increasing a certain percent every year or decreasing a certain percent. You know, like your home, you would like it to increase in value, and you'd like to see exponential growth there. Whereas most of the time when you buy a car, you have exponential decay where it gets less and less value and it also becomes a collector's item or something. So, our formulas for growth, you can see they're exactly the same, except this would be plus your percentage rate and this would be minus your percentage rate. Remember, anytime you put percentage rate, like if it was 15%, whether it's growth or decay doesn't make any difference. Remember, you use the decimal 0.15. So you move the decimal 2 places to the left no matter what we put in. So the values, the A of t in both cases is the final amount. The A is in both cases the initial amount. The R changes. In the case of growth, R is the rate of increase. In the case of decay, it's our rate of decrease. And time is the same. It's the number of time periods. And that could change. It could be hours, it could be days, it could be years, months. Whatever the problem will tell you what to use in that case. So we'll be using either this formula if it's a growth problem, or this if it's a decay problem. So, an example. Tony purchased a rare 1959 Gibson Les Paul guitar in 2000 for $12,000. Experts estimate that its value will increase by 14% per year. Use a graph to model when the value of the guitar will be $60,000. Okay? So in this case, we're working with a growth equation. So we're going to use this formula. If you look at our values here, our final amount's what we're trying to find. Our A is our initial amount, and so we paid $12,000 for that. So we've got our A of t equals the initial amount, which is $12,000. Times 1 plus our increase, which is 14% per year, so 0.14. And we don't know the length of time. In this case, it doesn't tell us the time. It wants to know when is this A of t going to reach $60,000. So we don't know what value we're going to have there. Now later in this chapter, we'll be able to learn how to find this exactly, but we want to know at this time, how long does it take for it to get to $60,000? So once you have the equation, then we can go to our graphing calculator. So let's bring that up. And if we bring up the graphing calculator, we just go to y equals so we type in the equation, 12,000, and then in parentheses, I'm just going to put add 1 plus 0.14, so 1.14. 2, and then we're just going to put in a variable for the exponent, x. We can enter that, and then we can graph it. Now we're going to have to look at the window on this. So we know we're going to be at 12,000 when we're at 0, and it's going up. So let's go, our y maximum, we got to go up to 60,000, so I'm going to make it 80,000. And let's go by 100. And if we graph that, so this is our starting point at 12,000 that the guitar is originally worth. And what we're going to do is we're just going to go to the trace function, and we're going to go along this until we get 60,000 here. So here it's 59,615, and here it's 62,000. So somewhere between 12.2 and 12.5 is when we hit it. So you can just estimate on this. It's going to take about 12.3 years before it reaches that $60,000. But again, you just have to determine the formula, plug in the amounts, and then use the trace function on the calculator to find out. So we can take this out and see when it's going to be 70,000. It's going to take 13.5 years. And you can see it's going to climb faster now. And it's going to get to 80,000 in about 14.4 years. So we can use the calculator, just type in the equation, type it into the calculator, and use the trace function to find when it reaches the amount you want it to be. So let's go and look at a decay problem. So here's an example that a lot of you see with vehicles that you buy, that the value will decrease as it goes through the years. So the value of a truck bought new for $28,000 decreases 9.5% each year. Write an exponential function and graph the function. Use the graph to predict when the value of the truck will fall to $5,000. So, if we go to our formula now, this would be f of x equals, or actually let's use the exact formula. A of t equals a times 1 minus r to the t power. So in this case, our initial amount is the 28,000. 1 minus, remember it's 9.5%, so you have to move the decimal 2 places to the left, get 0.095 to the t, and we want to know when is that going to get to $5,000. Okay? So you don't even have to subtract this. You can just go ahead and type it into the calculator that way. So if we go back to the calculator and go to y equals, and let's put in exactly what I've written here. 28,000, and then 1 minus 0.095, parentheses, to the x power. And if we graph that, I'm going to change my window again since we're starting at 28,000. So let's move that to 30,000. And let's graph that. So we get our graph. We do the trace function. And we want to know when that's going to get to 5,000. So between 17.34 and 17.0, and it's really close. It's 4,959 there at 17.34. So I'm just going to say 17.3 years. Now again, we're just approximating on these, but it gives us, again, you just choose the formula you need, you plug in the information, and you go from there. So, your assignment for 7-1 is page 494, 7 to 22 all. You don't need to draw your graphs on your assignment. You can just put them in the calculator and get your answers from there. But you don't need to take the time. I know you know how to plot the graphs. So just set them up on the graphing calculator and do the trace function to find your values on the ones where you need to. So good luck on that. Hope it helped. Thanks.